Okay. Oh, I didn't put an announcement out because I was just going to talk about it today. All right. So we're currently in module 5, structures and members. In module 4, if you go in there, oh, let me go into student preview mode. Go into student preview mode and go to module 4. I've done what I did before. I attached the answers to the homework. Normally I boldface this, but I forgot to do that. The homework solutions, I uploaded them actually this morning. I graded the homework, finished grading the homework last night. Pretty much there was 30% for, there were a lot of problems. So I gave 30% just for completion. In other words, now you got 30% if you completed all of them or made an attempt at all of them. Everything's sort of prorated, right? If you didn't do half of them, you only got 15% of this. And then the other 70% was split up as points between these problems. Now, the way I did the points is the first 1, 2, 3, I think the first 5 are all free body diagrams, which surprisingly, a lot of people did not do well on those. I didn't put very many points on them, so that was good for you guys. But you know, we need to review this again because free body diagrams are important for setting up and solving a problem. And I just want to go through some of the answers here because I want you to see what is missing. And so let's look first at the textbook. Problem 4-2. There were 2 places people messed this up. And oops. So AC. Now, in theory, you could have taken and put X and Y, but that makes the problem really, really difficult. The intention of showing the rollers here and the slope, and no one actually did X, Y at the pin, but you notice there's rollers against a surface, right? And no one messed up this one, I don't think. It's 90 pounds downward, right? That's the force. That's an external force. The reaction forces, however, they're not pointed up, and they're not pointed this way. The reaction forces are reactions from the surface of contact of these rollers. So they are perpendicular to the rollers. And the slope of a line that's perpendicular to another line is the inverse of that line's slope, right? So if this line is 1x, 2y, the line that's perpendicular to it is 2x, 1y. So let's look at the answer that I was expecting, which again, some people got, but a lot of people did not. Sort of rhymes. Something like this where you draw ABC, right? And you draw the 90-pound force acting downward. And you know, this didn't have to be exact. All you have to do is show me is the arrows of the force. And you need someone handed in a paper with no arrows for the forces. It's completely useless. It doesn't tell you anything about which direction your forces are going, especially the applied forces. The applied forces act in a direction. These forces act in a direction, right? Reaction from the surface out to the points. So you need to draw your forces clearly and differentiate them from things around them, like axes, right? Put some arrowheads on them. Otherwise, they're just, I don't know, lines with. Some people didn't even label things. I got some drawings that were just a sketch with sticks off of it. I'm like, what am I supposed to tell from this? Let's see. Number 4, I think it was. Oh wait, was that number 4? Oh yeah, number 4. What caused people problems here? Well, point A and B, and those were the two that caused problems. Notice we want the free body diagram of member AC, right? And that includes point B. Now, point B is some kind of pin joint. A has got a tension associated with it, right? There's a cord connected, so it's got tension. And the same thing over here. You're actually shown a force acting down at this angle or this slope 5/12, right? And if we go to the free body diagram, something like this. I was looking for you to recognize, and again, these don't have to be in the same direction as mine. You could have had your Y direction pointing down and your X component pointing to the left, but you need to recognize that at pin joint B, there's an X and a Y component of that force, that reaction force. Over at A, right, that rope is in tension. It's pulling on A. You can't compress a rope, remember? I mean, you can try to, but it's not gonna, you can't have a rope under compression. It's just not it's not gonna hold up. Right, it just kind of buckles. So you can carry tension in a rope. Let's see, so that's what I have for, I was looking for these 4 points. Let's look at number 6. Number 6 is a good review anyway. You're gonna have to draw a free body diagram on your test at some point. So, free body diagrams also include dimensions, right? Because the point of a free body diagram is that's what you're basing your analysis off of. Let's look at this one. This is 4-6. Free body diagram of the frame shown in figure 4-6. So this frame is connected to the rest of the world by, let's see, there's this pin joint on the wall over here. I must use my pen. There's a pin joint here on the wall. There is a roller down here at E. And then there's an external force acting at D. So when I go to draw that, right, at A, I've got a pin joint, so I've got reaction forces in both the X and Y direction. At E, I have a roller. So E is free to move left or right. The reaction force, the force that's opposing its motion, right, is from the bottom, right, the ground. It's a reaction force vertically, normal to the surface because it's on rollers. And then I've got this external force, 600 newtons. It looks like I actually might have forgotten, let's see, 3, 4. Oh, I drew this incorrectly. This 4 meters out to this point here, out to point D. Yeah. So this is actually incorrect. I got to redo this problem on the answer sheet, answer key. 4 meters goes out to point D here, not point C. And that's all you need to actually figure out these reaction forces. These dimensions that are given, plus my correction, plus the unknown forces. All right, number 9. Number 9 was supposed to be straightforward, but the picture, it looks like, confused some people. I'm going to zoom in here. All right. A jib crane supports an 80-pound load. Assume all surfaces are smooth, draw a free body diagram of the crane, and label all forces. Now, the thing that was weird about this one was the way this is shown at A and B. This structure here is not embedded in A or B. What it is resting inside of these, if you imagine like a pole or something, right? It's right resting inside of these holes. The 80-pound force downward is pretty obvious. Let's start with B. At B, obviously you have a reaction force from the ground acting upward, right? The other thing to notice is there's going to be some wall in the x direction that retains, keeps B in place from moving back and forth. So you can draw an x component constraint, right? An x reaction force. You have an x and a y. Those are reaction forces. Those are the forces that constrain this part of the beam, right? So that it can't move down through the ground, right? And it can't move left or right. Basically, x component, right? Now, the one at the top is a little different because the one at the top is not in contact with the ceiling. It's only held in place from moving left and right. So the constraint here is only an x direction force, right? An x direction reaction force. So you would draw something like this. There. So notice at B, I've got a y component and an x component. And then over here at the, obviously the external force is 80 pounds downward. And then AX is an x component. There's no y component on A. So that was really the only thing that kind of confused people that knew what they're doing. Number 20, again, a little more complicated. Oh, wrong page. For a free body diagram of member A, B, C. Oh, over here. So this is the problem for 4-20, free body diagram for A, B, C. I didn't really look to see, like some people included the pulley, some people drew it right from the point. Either way, I was fine with whatever. No dimensions were given about the pulley. So you really had no reason to draw it from the pulley, but whatever, if you did it that way, it was fine. You're given the slope of this thing, you're given an attachment point, pin attachment point, right? So here it can't move in the X or Y directions. Here you've got tension acting at B, and there's two forms of tension. There's two tension components, right? There's 20 pounds acting in this direction, basically straight across from B. There's also, because tension in a cord is continuous, right? There's also 20 pounds acting at this slope of 10-1, but it's acting in the direction to the left on this structure, right? This structure is being pulled in this direction by two tension forces, right? It's acting as the pulley, right? The joint location, but the tensions are acted along the cord, right? 20 pounds in this box along this line, or by the box, and then 20 pounds in this direction, right? So this is what gives pulleys somewhat an advantage, right? You're using the structure to support some of the weight. And then at the base here, this is a point contact, in contact with the surface. So the reaction force is going to be acting normal to the surface. And they give you a slope of 12/5, well, I guess 5/12, x, delta x versus delta y. So your perpendicular slope is going to be inverse that, right? It'll be 12x 5y. So let's look at the free body diagram for this. In fact, I wonder, see if I can do this. Same page. This might be more helpful to see it. Yeah. So notice for point A, right? I replaced the pin joint. Right. I replaced the pin joint with two. I feel like my pen should be able to go over there with two components, AX and AY. The tension at B. Again, no information was given about the pulley, but if people drew them that way, that's fine. 20 pounds horizontally. And T is the same, right? T is 20 pounds, T is 20 pounds here. Notice the slope 1 to 10. And then here at point C, I've got a force acting perpendicular to the surface at a slope of 5/12. And I think that covered the free body diagrams. Most people got the pulley problems right. I noticed people using interesting symbols. Look, if you're going online to figure out your homework, it's just going to hurt you in the long run. Most people, well, it seems like a lot of people are giving this a good shot, which is why I don't penalize a lot for incorrect answers. I'll look and see, what you did. Like here, you got to report tension and compression, right? That was part of the question that was asked. If people made mistakes, minor mistakes on their moments, I tended to just take off like a point here or there, depending on what the mistake was. Most people did their sum of the moments correctly. I used to have a professor in heat transfer. This was his quotation. This is what he told us after every test. There's no shortcut to proficiency in any subject. So he was apparently really upset about the grades that were on the test. But this is just, if you're trying to master a subject, right? Dr. Obat from Clarkson University, he's retired now. It doesn't matter what you want to do, right? If you want to become a good soccer player or a good baseball player or basketball player, whatever, you have to take the time and practice, right? You can't just walk onto the court or the field during a game and expect to play at the same level as everyone else who's been practicing for years if you've just haven't done that before, right? That's fairly obvious to most people in the context of sports. The same thing applies in the context of problem solving, right? You don't come to school to be, just like soccer skills or basketball skills, right? No one can just give you those skills, right? There's no magic potion for you. Like, you can't just watch someone play basketball and be as good as them just by watching them. If you sat down and just watched NBA games for a year, right? And then tried to show up on that court and do the stuff that they did, your body would be like, what the hell are you doing to me? I can't do this. It's all in your head. So you've got to get those neural pathways, going in that direction, right? You got to get your body used to doing that, those drills and those movements by practicing. Same thing with homework, right? That's the reason you're assigned homework. It's not so that I can sit here and grade them every weekend. It's and make spreadsheets up with your grades. The homework is there for you to practice and to learn the material, right? So, and the reason I'm also saying this is, yeah, people are turning to the homework, but I don't know. I'm trying to remember. There was a decent amount of people that just didn't bother to do the homework. And if you want to learn how to solve the problems, if you're going to be disappointed on a test because you didn't, get a good grade, but then you look and you haven't done any of the homeworks, or you did the homeworks but you just copied off of Chegg or something, well, that's your problem. Your problem is not that the material is hard. The material, yeah, it's challenging to learn, but the problem is not that you just don't understand it. The problem is that you're not putting any effort into practicing it, right? So don't expect to do dunks and layups on the test if you're not getting out there and doing the drills by doing the homework and trying the homework, right? It's one thing, again, if you use Chegg to sort of, or whatever other online resources you're using, if you're if you're trying to solve the problem and you're going through, and then you're like, let's check my work, right? And you check your work, and you're like, well, whoa, well, that answer doesn't make sense. What did I do wrong, right? And then you go back and you look, and you see, oh, you know, I made a mistake here. That's doing the problem and learning, and going back and doing it again. But you have to struggle through this homework to actually get good at doing it, doing the problem. So that's my little spiel on homework and such. Are there any specific questions on homework 4 that you want me to go over now? Otherwise, oh, this answer key has an extra problem in here which I didn't assign. I just left it off. So if you see this and you get confused why there's a 57, it wasn't assigned. All right, so that's mod 4 homework. Let's go back to mod 5 then. And everything's cumulative, right? So you're building on all the stuff you learned in chapter 4. You can see just from the example, the first examples we did the other day, they're coming back and you're using them to do the analysis of method of joints, you know, the structures and the joints that support each of these structures. All right, so today we're going to talk about method of sections. So we just finished method of joints, right? And method of joints was interesting because it allowed us to take and figure out for every single member here, right? By doing a force balance on the appropriate joint, right? We could figure out what the force of each member was and if that member was in compression or tension. However, sometimes you might have a pretty big truss and maybe you need to figure out the forces just in a few of the members near the middle of the truss, right? And method of sections is very useful for that because what we're doing, we're just cutting it in half and we're cutting it close to or through the members that we want the forces, right? So we're going to cut through the members of who we want to find forces of. And then we're going to use free body diagrams of each of those sections to find those forces. This is pretty much what we're doing for non-concurrent force systems. So systems where, well, when we say planar, we're talking about 2D systems, but non-concurrent is also where the forces, the lines of actions of the forces do not intersect, right? Now, sometimes they do, or sometimes a few of them do, but not all of them. All right, so let's see. Some of the tips for method of sections. Obviously, the first thing you do is you look at the entire truss, right? And what's the free body diagram for that truss? And when I say free body diagram, I mean, okay, if you were to take and detach that truss from the rest of the world, what are the support reactions, right? What are the forces that are acting on this truss? There's obviously, you know, external forces and then support reaction forces. So once we do that, we'll have reaction forces. Then we cut the truss through the sections of the members where we want to find the forces. And then we're going to draw a free body diagram of the section and solve. Now, we're going to have two sections here when we cut it. And there's a way to, there's an easier way and a hard way, right? Depending on which section you choose. One section might give you more, or may give you an answer quicker than another. Good rules of thumb here. Don't cut more than 3 members at a time. And just like we did with method of joints, assume all the forces are in tension, right? And again, if they're not in tension, you'll just get a negative answer and you can repair that on the fly. So let's see, is this is actually pretty close to the, well, it's in metric. This is pretty close to the first one that I do with you, the first example. But here's a simple illustration, right? We've got this this strut here, and it's It's pin jointed against the top wall. It's got a roller joint here. So based on the pin and the roller joint, we can figure out these reaction forces, and obviously the 1,000 newtons. We can figure out the reaction forces at each of these attachment points, right? And that's going to look, we're going to set up a free body diagram like this, right? dy, dx, ex. If we want the forces, though, in these three members, once we get these reaction forces, we're going to make a cut through here. We're going to look at this, and we're going to say, okay, I want to figure out these forces. This is its own free body diagram, right? Just like this attaches to the rest of the world here, right? ABG attaches to the rest of the world through these three members, right? So this is a static body. So you can do the statics analysis on this. And one thing to notice about this problem is you don't actually need to know the reaction forces over here at D and E, because this is its own free body diagram. And you can find the forces in each of these members just based on this geometry and this one single force here. And we'll figure out how to do that in a minute. All right, so this is the first one, number 3 here, example 3. This is the one that, again, is very similar to the one we just saw, except it's in US units. Determine the force in members BC, CF, and FE. And also mention if the members are in tension or compression. So we're going to cut this right through these 3 members of interest, and we'll see how we can get the information for that. And then this one's a little more complicated, so we'll get to that when we get to it. Oh, I got to zoom out from our homework examples. All right. The first thing I want to do here is I want to look at this thing. I want to say, okay, we're going to cut this. I could draw the full free body diagram, but I'm going to look at this first and see, does it make sense? If I want the forces in these 3 members, I've already got a force here and a force here. This is its own static structure, right? And the way that it attaches to the rest of the world is through these forces EF, CF, and CB, which we're going to assume initially are all in tension. So I'm going to take look at right-hand side, right? And I'm going to draw a free body diagram of this. Oh, it's 4 and 4, so it's a fairly, oh, I got to draw the triangle a little better. This is 4 feet. And this is 4 feet. We've got our forces acting here. We've got 800 pounds acting downward. We've got 600 pounds acting down over here. And let me label my points too. This is point D. This is point E up here. And then we've got point C in here. And you'll see why I'm putting the C in there in a minute. Because the other forces we have are up here at E, we've got force EF. And it's helpful to label the forces by the letters in the direction that they're going, right? So here from E to F, right? That's the force between E and F. Down at C, we've got two forces. We've got CF and then we've got CB. So notice, I don't know for sure the directions of these things. I'm just drawing them all in tension. I don't know that they're in tension. I'm just drawing them that way. Let's see, I've got 4 feet, 4 feet. Yeah, that's pretty much all I need. I mean, you could put you could put the length here of the hypotenuse, right? 4 square root of 2 feet for the hypotenuse, but that's something you can calculate. Okay, so now we've got this free body diagram, and we say, how the heck do we do this? There's a few different ways you can do this problem. Is this the easiest way? Yeah, it's probably the easiest way. The first thing we want to do is we've got 3 unknown forces here. It would be nice if we could do some equation that eliminated 2 of them and left us 1. Does anyone have an idea what that would be? Muted. If we took some of the moments about a certain point, we could eliminate lots of forces. Let's look at point E. If we took some of the moments about point E, we would have CB, and we'd have the X and Y component of CF. So that would still give us 2 unknowns. Let's see. If we did about D, we'd still have all these 3 unknown forces, right? If we took it about C, we'd have these 3 unknown forces act on the point of rotation, right? Distance is 0. And we'd have 1 unknown and, well, just 1 known over here. So I'm going to start with, let me just put a comment. Look to try and minimize number of variables. Use some of the moments, in this case, about C. So some of the moments about C is equal to 0 is what we're starting with. We're going to use the, again, counterclockwise convention is positive. So about point C, we've got basically 2 forces left. We've got EF, and EF is going to make a counterclockwise rotation moment, right? So we've got EF, force EF, times the perpendicular distance of 4 feet, right? And then over here at point D, we've got 800 pounds acting downwards, and that's generating a clockwise moment about C, so that's a negative. Oh, did I say 400? 800. I don't know what I'm saying anymore. 4 feet, 800. And that's at 4 feet as well. So solving this equation, we find that FEF equals 800 pounds times 4 feet. So up here we've got pound foot divided by 4 feet. FEF is equal to 800 pounds. And is the member in tension or compression? In this case, we drew it in tension, we set up the equations and treated it as if it were in tension, and we got a positive value. So it is in tension. So that's what the answer here to that one is. So force EF is 800 pounds, and that is in tension. Remember, we're doing the analysis on this as a free body. We're not looking at a specific joint or a specific member. We're looking at this entire structure. And these reaction forces are the forces in those members. We cut them right, we cut them in half. All right, so the next one is, we used some of the moments already. You could use some of the moments again, but now we can just start breaking this down into X and Y components. At this point, it really doesn't matter which you take first. Well, yeah, it really doesn't. I mean, you're going to have X and Y. If we take Y components first, we're eliminating FCB, and we're keeping FCF, at least the Y component of it. So it does actually help you to stick with the Y components, because otherwise you'll have two unknowns again. So the next step would be sum of the forces in Y equals 0. And that's going to be positive in the vertical direction. So what is this? This is 0 equals, what are the Y forces? We've got the two applied forces are in the negative Y direction. So we've got minus 600 pounds, minus 800 pounds. And then FCF is in tension here. So the Y component of FCF is the vertical component. And everything we're given is a 4 foot by 4 foot triangle, right? So we're going to have plus FCF. Now you can do this a number of ways. You can say it's a 45-degree angle and take the cosine of 45 or the sine of 45. It doesn't really matter at this point. If you're looking at this triangle, right, the Y component for this triangle, it's going to be cosine 45. The Y component for this triangle is sine. But I'm going to use a ratio because I know 4 and 4 square root of 2. So I'm going to say it's equal to FCF is the hypotenuse, right? And the Y component of that is 4 over 4 radical 2 of the hypotenuse, right? They're similar triangles. So this gives us an FCF of, what do we got? We're going to divide through, we've got 1,400 pounds times, we've got basically radical 2. These are in feet, they're just going to cancel. So now we've got FCF is equal to 1,980 pounds. And that is also in tension because we got a positive number, right? We assumed tension. We calculated it as if it were in tension, and we got a positive value. All right, last component, let's see, EF, CB. So some of the forces in X now. All right, so notice CF has an X component, but now we know CF, so we know how to find that X, or we can find that X component to a numerical value. EF is also numerical, so the only unknown here now is CB. So let's do sum of the forces in X equals 0. And let's look at what we have for an equation. We've got 0. Oh, let me also draw X, right, is positive in that direction. All right, let me just zoom out a tad more. Okay. X direction forces. We don't have too much. We've got EF is 800 pounds, but notice that's directed backwards, right, to the left. We set it, so this is also now where to start thinking about what tension means, right? Tension is pulling at that point, right? So that's a negative 800 pounds. Let me just make a little note here. This is your FEF. FCF is also in tension, which means, again, if you draw a force triangle of this, that's a positive Y and a negative X. So that's another negative. And here we've got FCF. And to find the Y component, again, you can use sine cosine, you can use the ratio of the similar triangle heights. Right, this is FCF X component, right? This is the X component of FCF. And then we've got minus FCB, right? Because FCB is unknown, but it is an X direction force. These two Y forces are not even part of our analysis. If you do the math here, you wind up with minus 9, or FCB is minus 800 pounds minus, what did I get for this? Oh, well, let me just do it. 1980 divided by square root of 2. Yeah, it's something, yeah, I just wanted to see how close this was. It's like 1400.07, so I'm just going to leave it as 1400 pounds. And that equals negative 2200 pounds. All right, notice the negative sign. So we drew tension. Calculated or set up formulas, right? So the negative sign indicates the reverse assumption. So this is in compression. So I'll write that over here. FCB is 2200 pounds in compression. Now, the other thing I saw in the homework, not too much, but just occasionally, if you're going to report a force, have a direction, but don't report a sign and a direction. In other words, negative whatever 60 newtons up is, well, negative, I guess negative 60 newtons down Well, that's kind of redundant, right? Maybe you've used y-axis as positive upward, right? I don't know necessarily what axis you use for your calculations, but when you report a force, you report the force, the magnitude, and its direction. And for these members, the direction is compression or tension, right? We know what they look like in the context of the strut. We're not going to say left and right, 90 degrees, up and down, 45-degree angle. We're going to say the member itself is compression or tension. The forces themselves are acting on the joints. That's what we're doing the analysis on. So just make sure you use the minus and plus signs to recognize, and then make sure you report compression or tension, because you may make a mistake, or you may do things completely backwards and just assume everything's in compression. And you'll wind up with negative numbers up here and positive down here. If you just report negative, negative, positive, I'm not going to know what that means, right? I'm just going to assume, well, negative must be compression, and they messed up the signs here. So just report it as tension or compression. A T and C is fine. All right, what time is it? Oh, 12:46. Does anyone have a question about this method of sections? I thought I would get farther, but I think what I'll do is I'll just end here. I'll take any questions, because I don't really want to start starting the next one is kind of like, yeah, we're going to get right into it. So I'd rather just postpone it till next time. We'll work on that. I talked a little bit today about homework, so that took up more time than I expected. So we'll do the next one on Wednesday. Any